My name is Stephen Emmett. I'm the head of Microsoft's Computational Science Lab, which is based here in Cambridge. The lab does the science, builds the tools and builds the models necessary to solve some important problems in science, whether it's how the immune system works, all the way up to the other end of the extreme of natural systems, of how the climate works and how the planet's ecosystems work, and how future predicting how future perturbations to such systems might affect the planet, particularly human perturbations, human activity. My colleague Drew Purvis leads the computational ecology group, and Drew's going to be talking particularly about one aspect of the work of the computational science lab, which is on sort of information about the planet. So our title is, as I say, this is going to be brief. Drew's doing the interesting bit. Our title of our brief talk is From Big Data to Big Decisions. Technology companies, our own included, Microsoft, but also to name just a few others, Facebook, Google, Amazon, are all competing for an enormous market for information about people, consumers, predominantly people online. But there's a different market about to emerge, which is a market for information about the planet, about the future of carbon, about the future of the climate, about the future of food and water, about the future of extreme weather events, and about the future of human activities and their impact. And I think that it's becoming increasingly clear that this market, the market for information about people, has the potential to be at least as important and possibly, potentially, far more important than the current market that technology companies are chasing, the market for information about people. In fact, it's almost certainly going to drive the future of almost everything. It will drive the future of international government policy and decision making. It will drive the future of enormous sectors ranging from insurance, energy, the global agriculture business, to name just a few. And the interesting thing about this market is it's not just driven by big data, it's driven by big science, or probably more accurately, I would say, by new science, new kinds of science. And by that I mean a new science that enables a better prediction of future climate, and science that enables a better prediction of the future of carbon, and enables a better prediction of the future of the planet's ecology, which provide ecological, or what's called ecosystem services that we rely on for our well-being on this planet. All the way through to a new science that enables a better prediction of whether we're able to predict and prevent, or at least manage, a global pandemic, which most epidemiologists are agreed is a matter of when and not if. Could be tomorrow, could be in 83 years' time. The issue about that is this requires this kind of science that's necessary to underpin this market for information about the planet. Not only requires this kind of new science, it requires something that's currently really very, very difficult to do, which is the ability to build and integrate complex models about complex systems, because all of these things are about complex systems. And what Drew's going to talk about, and that's going to be necessary to provide what you might want to call actionable information about the planet for citizens, for businesses, for policymakers. And Drew is going to give us an interesting brief glimpse into some of the new science, the new models and new tools that we're developing in our lab that Drew's leading, which is really kind of underpinning our ability to, and I think Microsoft's future ability to be at the forefront and pioneer this new market for information about the planet. So over to you, Drew.
All right, thanks, Stephen. I'm going to try and keep the time as well. Now, I think I've probably met maybe half, maybe even more of you actually already at the booth that I'm manning, which is a demo of a prototype tool for this big data to big decisions pipeline as applied to the environmental sciences. So anyone that hasn't come along, I'd encourage you to come along and chat to me at the booth. There's a booth next to me, so the story of that booth is very much about tools and tech. But now on here, I should have my research next PowerPoint. Let's have a look. Slideshow, current slide, okay. Reflects one half of our group's mission, which is about the tools and tech, how we're trying to create new software tools to enable this new kind of science to underpin this new sort of information about the future of the planet. The other booth is about a thing called the Madini model, which is a very ambitious, far-reaching scientific project about doing an individual-based model of all the ecosystems on Earth. That's modeling every multicellular organism, every little rotifer and aphid and snake and fox and so on across the whole world. See if we can understand how the structure and function of ecosystems globally has emerged from all of that. So that's the booth next to mine. So Stephen introduced this idea then of information about the planet, building complex models, using those models to create actionable information. And so what we mean by that really is you can think about the idea of defensible predictions. In other words, you're making some prediction about something that's really important, like how agricultural yields might respond to fertilizer application or something like this. For those predictions to be defensible, we need to be able to explain how it is that we've actually come to those predictions, A, and B, we need to explain the uncertainty on them. And many examples of bad environmental decision-making come from one or two of those, using bad models or not making a decision that includes the uncertainty. Now, the good news is that we now have, I think, an agreed philosophy, really, about how best to go about building defensible predictions of the future. And I call this the defensible modeling pipeline. And the idea is we start on the left here, and this is the big data story. So we have our data, but we also have ideas about how the world works, hypotheses. When we're predicting, that is, we're either going to places that have never been seen, but even more if we're going into the future, a time that has never been seen. It's very, very important that we build in all the knowledge and understanding and the science about how the system works. We can't just throw that data through a standard kind of black box machine learning algorithm. What we need to do is build complex ideas about the way the world works and collide that with the data. So we have the data here, and then the step here is this Bayesian inference step. And so we mash it through the Bayesian inference. And what this leads to is a refined idea about how the world works. So we throw away some of those hypotheses. We understand the world better, and that's the main thing, actually, in the long term that matters. At the same time, though, these models have these numbers in called parameters, these constants, and we're able to estimate those. Now, with an idea about how the world works and the parameters, we're then able to make predictions that include uncertainty. So that's the kind of defensible, the Bayesian modeling pipeline. Now, this step of the Bayesian inference here, I think there's a nice analogy with CERN, which is at the same time that those scientists were spending billions of dollars building that amazing thing called CERN, which is an incredible scientific endeavor, there were these much less charismatic scientists working out how we could do this kind of Bayesian inference on complex models. How could we take a really complicated model, like a model of how ash dieback might spread in Britain, or malaria spread worldwide, or bird flu spread worldwide, or fires, complex model like that, and mash that up with huge amounts of data. And we now have ways of doing that. So in those last 15 years, computers have got faster, and we have agreed methods. And these are absolutely revolutionary for the kind of environmental science that I do. Every bit as revolutionary as a giant particle accelerator. They quite literally let us take ideas and data and smash them together, and what comes flying back out is an increased understanding about how the world works and predictions that we can defend. We can also, of course, feed back from the end of that to say, now we understand the uncertainty in the models, we can work out what data to go for next, which data would give us the greatest improvement in the model predictions. So that's all well and good. And just to give you an example here, so one of the things we've done is we've applied this Bayesian modeling pipeline to the global terrestrial carbon cycle. That is all the carbon that's held in trees and in soils across the world. Now it turns out, and here comes the science bit, concentrate, etc., that of the CO2 that we put up in the air, half of that CO2 is sucked up by living organisms. Half of it on the sea and half of it by trees, primarily on land. That means that the problem of climate change is only half as big as it would be because of this huge favor that's being done by the vegetation and the oceans. However, there's a huge amount of uncertainty about the future of that so-called carbon sink. In fact, it's the largest source of uncertainty in the future climate. Will the carbon sink get stronger and therefore act as an increasingly efficient brake on climate change? Or will the vegetation turn into a carbon source and act as a turbo boost on climate change? Now, the reason there's so much uncertainty is because people have built models of that process, but they haven't put those models through the defensible modeling pipeline. Instead, they've taken ideas, preconceived ideas, and they've taken their best human guesses at the numbers and put them together. And what you get is a prediction. And several different groups have done this, and the predictions are really different to each other. And so those models haven't been constrained by the big data as we want to see in the Bayesian modeling pipeline. So what me and my colleague Matthew Smith, who's not here today, did was we built a new model of the terrestrial carbon cycle, but then we pushed it through that Bayesian modeling pipeline. And what it led to is this. Now, obviously, you won't understand the details, but the point is this is a model about, on the left here, the atmospheric CO2, how it cycles into the plants through photosynthesis, gets allocated to stems, roots, leaves, and so on, which die and come down into the soil here and eventually make it back into the atmosphere. And at each step, the allocation, the photosynthesis, the soil respiration, all of these things are sensitive to the climate. And those climate sensitivities are unknown, which is why we had this uncertainty. So we pushed it through that defensible modeling pipeline, and now we're left with this, which is a fully defensible, properly data-constrained model of the terrestrial carbon cycle, the first one. Now, because of that, we're able to make predictions like this, which is we're able to go across the world and predict the potential carbon storage at any point just based on the climate, again in a very defensible way, again with uncertainty. And you can imagine what that could mean in a market for carbon storage, as might be enabled by these so-called red schemes. This might be enormously important to the economies of these countries. We can also make a prediction like this, which is the future of the terrestrial carbon cycle out to 2200. The lines there are best guesses, and I won't explain what the three different lines are, but each one has uncertainty. And we can see there's a lot of uncertainty, but we can be sure, according to this, that by 2200, unfortunately, the vegetation will turn into a carbon source, according to this model. So unfortunately, the turbo boost scenario looks like it might happen with some level of certainty. So that's fine, but the thing is, Matthew Smith is really, really clever and really, really technically savvy. And it took him 2 years to do this. And as long as that's the case, we're not going to be able to do this kind of defensible modeling of these complex things in general. We're not going to be able to make these predictions quickly enough. So what I wanted to show you, and I'll finish this off at my booth, so I will just carry on going until Rachel nods at me and I'll just stop. That's fine. There's no special time to stop, really, for this analysis. Is what we tried to do then, using the fact that we're at Microsoft, we can imagine and engineer much more ambitious scientific tools to enable this kind of work. So we've got this thing. It's currently called Boop, which is a name that I'm not allowed to use, so it would be great if no one could use that name. I was thinking maybe this morning, actually, of maybe OmniShambles would be a really good name. It's got a nice ring to it, hasn't it? But anyway, so maybe it will be called OmniShambles, because it's a very trendy word, according to the BBC website this morning. So here, this is simply a browser application. I had nothing to download. I can go in here, and I can do an action, which is to import a file. And you'll be blown away by this. So we go and import the file, and then we can look at the numbers in a table. Isn't that just incredible? And the point is, this is a really simple file that just has lat, lon, and the yield of wheat in this particular example. Fine. But the thing is, we can instantly now spring off another action, which is to create a chart from that. Again, just all within the browser. And if we do lon, lat, and wheat here, we can straight away look at how the yield of wheat varies across the world. What's happening here is this thing is all metadata here. I can add notes, and I can add various attributes. And the provenance, there's a workflow being built behind the scenes here, which is tracking what I'm doing. And if I change the data at the start of that workflow, everything downstream will be updated. So I'm going to speed up a bit now. I'm going to go back to my original file and do a fetch climate step. And this is going to go down the lat-lon positions, and it's going to use that to hook out the typical temperature for each of those locations. That's here. I can put that on a chart too, and say, let's have a look at air temperature and wheat yields now. And I can see that wheat yields tend to peak at an intermediate temperature. And then what I can do, I can go on, and at some point I'm going to stop, but you can find the rest. And I know some of you have already seen some of this as well, so I'm sorry about that. But I'm now going to build a model. So what I'm going to do is create an idea about how the yield of wheat is related to air temperature. I'll do this in the browser. And this particular idea is that wheat yields peak at intermediate temperature. That's what this so-called functional form shows. Don't worry about the details. The point is, I was able to bring in an idea into the analysis. Now, importantly, our idea is not limited by this point and click, because what's actually happening is there's code being built in the background here, F# code. It's a code that actually came out of this lab in Microsoft. And I can edit that directly. So I can actually put any model in there. I could put a complex biological process-based model about how I think the world works in here, any model whatsoever. A model about how wind speed and the time of year affects the spread of ash dieback disease, and anything you can imagine, in principle, could be put into that box. I'm going to go back to the designer. And then I have these parameters here. So that, which I mentioned before. And what we can now we have the model, we can spring off and train that model against the data. So here's my observed yield, here's my environment, which is just here. And then what's happening here, this is this particle accelerator step. So we're now combining, the idea here is at the bottom and the data's at the top. Those things are being collided, mashed through what's called an MCMC Bayesian analysis. So this is a fully blown, this is like, and what's come smashing out the other side here is a bunch of these parameters. And we can have a look at those parameters if we want. We can analyze them. We can get the uncertainty on the parameters, et cetera, et cetera. And with those parameters, I can actually then go and do a simulation under the same model and the same environmental conditions, which is here. That will create me a simulation now. So this is now my model simulation of the yields, which again I can throw straight onto a chart. Oh, I need just one extra step here, sorry. So I can do lon lat. And my predicted, not the actual yield of wheat. It looks very bad at the moment. That's because my model isn't very good. I didn't leave it long enough to train. But the point is, everything I've done here would have taken a huge amount of effort, even for the very best environmental scientists that you could find at the moment. Those steps of pulling out the environmental data, I didn't have to supply it, remember, of visualizing the data, of defining an efficient MCMC algorithm to parameterize it, making predictions with uncertainty would take a huge amount of time, even for the experts. I was able to do it in a browser in about 5 minutes. I can look at the provenance of this thing now. Obviously, it's getting quite complex. And the idea would be that I can take that whole thing now and if I hit this, I store the entire workflow as a zip file. I can then close down the browser, email it to you. You can go to this URL, which is already open, read in that zip file, and you're exactly where I am right here on this computer. And you can redo everything I've done. So you can convince yourself that I'm not an idiot. So you can work out whether you should believe my model. You could put more data in. You could change the model, et cetera, et cetera. So that's the way our thoughts are going at the moment anyway, about how we can build these useful pieces and put them together in a way that is, potentially, the argument would be, could radically accelerate and transform predictive modeling of the environment. And I will stop there. Thanks very much.